let's say we have three forces. We'll call them force 1, which is a vector and is equal to 2.00I plus 2.00J, and that's in newtons. We'll have force 2, also a vector equal to negative 4.00I plus 3.00J, also in newtons, and force 3, which is equal to 1.00I minus 3.00J, again newtons. Let's say these three forces are the only forces acting on an object. We know some things about what happens to that object. We know that the acceleration of the object is equal to 1.25 meters per second squared. Now, we only know that that's the magnitude of the acceleration. At this point, we do not know the direction. So I have the double lines on either side to indicate that this is the magnitude of the acceleration. We do not know the direction. We also know that the initial velocity of the object is equal to 5.00I meters per second. I'm looking for several things. Part A, what is the direction of the acceleration? Part B, what is the mass of the object? And part C, what is the velocity of the object at 15 seconds? So again, we have these three forces. These are the only three forces acting on the object. We know the magnitude of the acceleration. We know the initial velocity of the object. We're looking for the direction of the acceleration of the object. We're also looking for the initial velocity and the velocity at 15 seconds. James.
Couldn't you add force 1
To get what?
to get the net force?
Okay, so we could add all of them together to get the net force. Sure, let's see what happens. Force 1 plus force 2 plus force 3. Can you please read them to me, Sydney? I can't, they're far away from me. Force 1.
2I plus 2J. Negative 4I plus 3J. 1I minus 3J.
Okay, combining all our i's and j's, we have 2 minus 4 plus 1i, and 2 plus 3 minus 3j. So we have, let's see, this looks like negative 1i plus 2j is our net force, yes? Okay, we figured out our net force. It's not anything we're looking for specifically, but perhaps it's helpful. Again, we're looking for the direction of the acceleration, the mass, and the velocity. David.
Draw a triangle with that, or find the resultant force.
Okay, how do I figure out the resultant force? Actually, dare I say this is the resultant force? I mean, this is
Well, yeah.
the net force.
Yeah, but actual number value for it.
Okay, you want the magnitude of it.
Right.
Sure. How are we going to figure that out?
Square root of 1, or x squared plus y squared. So the square root of 1 squared is 2 squared.
I feel like I just fell down the stairs. Does anybody else feel that way? A little bit? A little bit. Where'd you get that from? I have no idea.
So you find, alright.
That's what I said. Where'd you get this from? I do understand that some of you are in a tendency to skip steps, right? But I will stand in front of you and I would do this. You see me? I take every step. Every step! Because if you do not take every step, you will fall down the stairs. If you fall down the stairs, this will be ugly. I will be at the top of the stairs. I'll be looking down. I'll be like, you are bleeding. college janitor to use his PPEs to clean up your BPs. Yeah, BP. There are too many acronyms. I did my bloodborne pathogen training recently. Show me what steps he's skipping. The Pythagorean theorem. What is the Pythagorean theorem? I mean,
A squared, B squared.
we have this equation, a squared plus b squared equals c squared. So if we look at our triangle, sure, let's see, -1 and +2. So we have a net force in the x direction. We have a net force in the y direction. We could figure out the net force. Using the Pythagorean theorem, we would have that the net force squared would be equal to the net force in the y direction squared plus the net force in the x direction squared. Therefore, the net force would be equal to the square root of the net force in the y direction squared plus the net force in the x direction squared. Naveen, is that what you meant?
Yes.
Oh, good. Net force is 2, which we're going to square, plus in the x direction -1, which we square. We take the square root of that. We have the net force, which is equal to square root of 5, whatever number that works out to be at this point. It doesn't really matter. We'll just leave it as a square root of 5. Perhaps at some point we'll figure out what it means. Okay, I'm going to return back to our question. We're looking for the direction of the acceleration, the mass, and the velocity at 15 seconds. J.
Well, right away we can solve for part
Okay, how?
which is the net force equals mass times acceleration.
Okay, so for part, well, we know net force equals mass times acceleration. Go ahead.
So then we write the equation as mass equals net force divided by acceleration.
Sure, we can do that. Keep going.
And then
I'm trying to see where you're going. I'm trying to decide what exactly I'm going to do.
and substituting the magnitude of the acceleration and the magnitude of the force to
Okay.
get the mass.
Okay, so we could figure out the mass here by using the square root of 5. I'm just going to do it this way. Square root of 5, which equals the mass multiplied by the acceleration we know is 1.25. Therefore, the mass is going to be equal to the square root of 5 divided by 1.25. True.
Equals 1.7889 kilograms.
Okay, so mass then as an answer, 1.79 kilograms. Great. I agree with that. That's the mass. Now, other thoughts. We figured out the mass. We've done part B. We need part A. Ms. Martin.
Well, since mass times acceleration, what
I'm sorry. Since the net force, which is a vector, is equal to the mass times the acceleration, which is also a vector,
then the directions should be the same.
Newton's second law. The sum of the forces equals mass times acceleration, where force and acceleration are both vectors. I've asked for the direction of the acceleration. Well, that's the same as the direction of the net force. Because if you take an acceleration, multiply it by a scalar, it doesn't change the direction. So all we need is the direction of the force. How are we going to figure out that, Con?
To find out the direction of the acceleration.
To figure out the direction of the acceleration, we're going to use the direction of the force, yes?
Yes. So shouldn't we well, we already have a triangle drawn, so we can use trigonometry to find the theta.
Sure. So here's theta. Go ahead, Con.
So.
That would be fine.
Oh, okay, yeah. So sine theta equals to opposite over hypotenuse, and opposite is, in this case, it's the force in the y direction.
The net force in the y direction.
So that would be 2.
We'll get to numbers in a minute.
Okay. And hypotenuse is the total resultant force.
The net, just the net force without acceleration.
Okay,
Great.
so that's equal to 2 over the square root of that.
Yeah, we'll get to numbers in a minute. So the theta then is equal to the inverse sine of the net force in the y direction divided by the net force. We have both of those. So the inverse sine of, as you said, the net force in the y direction, which was 2, divided by the net force, which we figured out to be the square root of 5. Theta then is equal to
63.434.
Therefore, that's in degrees. Therefore, what is our answer for the angle, please? answer for the angle. Justin.
The answer for the angle would be 63.4. Degrees.
Bart.
North and west.
We could do north of west, although in this particular case we are talking more about the quadrants, so positive x, negative x, so on and so forth. So the way I would describe it rather than north of west would be, Cheryl?
I was just going to say negative, but.
That's not going to be good enough. So what this is going to, I would say, is above the negative x-axis. Because in this particular case, it's not given in terms of the cardinal directions. Instead, it uses the I and j. The unit vectors have to do with x and y. All right, so far, we've figured out the direction of the acceleration. We've figured out the mass of the object. Let's back up a second, though. We already determined that the direction of the force and the direction of the acceleration are in the same direction. Are the direction of the acceleration and the velocity in the same direction? Are the acceleration and the velocity in the same direction? Landon?
No, well, not necessarily.
Actually, you can say no at this point. Why? How do we know in this particular case that they are not going to be, nor will they ever be, in the same direction for this particular example? Go, Cheryl.
Because you're given with the direction of the velocity initial.
True, so what does that mean?
So it's not in the same direction.
True, I agree with that. You can see the initial velocity is not in the same direction, but why won't it ever be in the same direction? Josh? The direction of what is constant? The direction of the acceleration is constant, true. What's going to happen to the direction of the velocity? As time goes by, the direction of the velocity is going to get closer and closer to the direction of the acceleration. The limit, if we were to get to time t equals infinity, would be that the velocity and the acceleration are going to be in the same direction, true? Will we ever get there?
No.
If we wait long enough? No, we still won't. It just doesn't happen. Okay. Under what circumstances would the velocity and the acceleration be in the same direction? Sam?
If velocity initial is 0
Or it happened to be going in the same direction. Or opposite. I suppose it could be going opposite direction and then eventually it would go in the same. The most obvious one would be if the initial velocity were equal to 0, then the velocity and the acceleration would be in the same direction. Good. We're getting there. We're looking for the velocity at 15 seconds. Velocity at 15 seconds, please. Sure. I'm sorry, Cassie. I try, but I have so many names. Carol.
The velocity equals velocity initial plus acceleration as a vector times the change in time.
Actually, you could do, these are all vectors, right?
Yeah.
Okay.
And then we have
Okay. We have this equation. We can use them as vectors, but we have a problem with everything that we have on the board trying to shove it all into there. What is the problem we have right now with trying to shove the variables we have into that equation? Goolsby.
Is it because the acceleration is written in vector form?
Well, the acceleration is not in
Yeah.
vector form, but the
Velocity.
velocity initial is in vector form, right? So that's the problem we have right now. So let's get the acceleration in vector form. How are we going to get the vector form of the acceleration?
Can we just take that the force being determined in like the component forms and divide by the mass?
We have this equation, Newton's second law, net force equals mass times acceleration. We have the net force and we have the mass. So the acceleration then is just going to be equal to the net force divided by the mass. The net force is, where is it? negative I plus 2j divided by the mass, which we got to be 1.7889. The acceleration then is equal to in vector form. That's in meters per second squared. So we now have the acceleration as a unit vector. We can figure out the velocity at 15 seconds. It's going to be equal to the initial velocity, which we have of 5a, plus the acceleration, which we just figured out, negative 0.559 I plus 1.11801 j multiplied by our time of 15 seconds. The velocity at 15 seconds then is equal to 5I. Multiply these out, please. $8.385I.
Plus 16.771 J.
Great. So the velocity at 15 seconds then, so is going to be negative 3.385 I plus 16.771 J. And our final answer then, the velocity at 15 seconds, it should be negative 3.3.
There's something following.
Thank you. 9 I plus 16.8 J meters per second. And that is our answer. We don't have to figure out the magnitude and direction. This is a good answer for what the velocity is. It includes the unit vectors, and that's a fine answer. You could figure out the magnitude and direction, but you would not be required unless specifically asked.